Welcome to the last day of class for the semester. The final exam is, I believe it's Monday. Yep, Monday, May 10th. And it'll open up then, and I'll be on Discord then, but we probably don't need to really communicate during the final exam. But in case you have any questions that come up, I'll be checking on Discord periodically. And so the practice quiz is just one question today. And the question is, what do you need to remember for the final exam? So I want to get one suggestion at a time. So anybody has an idea of what's something, and you can go in order. What did we do towards the beginning? You don't have to, but it might be a reasonable idea to kind of try to remember what did we do towards the beginning of the semester, and what do we need to remember on that topic. So anybody wants to lead off? Just go right ahead. What do I need to remember for the final exam?
Maybe just like general working with vectors. So that includes like, dot product, cross product.
That's what we started the semester with.
Yeah.
Dot product and cross products.
And also maybe adding and subtracting and stuff like that.
Adding and subtracting. All right. And on this topic, just to yourself, and you don't have to write it down, you can think about it. The dot product of two vectors, u dot v, tells you what about the vectors? The cross product of two vectors, u cross v, tells you what about the two vectors? So let me give everybody just a brief minute to ponder that for themselves. Okay, anybody want to put it in words for us? The dot product tells us what?
The dot product tells us, measures how close two vectors are to being parallel, and it returns a scalar value.
Very good. It tells us how much they're going in the same direction or going parallel. Very good. And the cross product tells us what?
How much two vectors are perpendicular, by how much two vectors are perpendicular to each other, and also it returns a vector value.
Scalar value versus a vector value. Those are answers that are relative to what?
On a plane.
How perpendicular they are.
Angle.
Okay, and if u dot v is equal to 7, what does that mean? Are u and v pretty parallel or perpendicular?
We would have to know the values of both u and v.
What do you need to know about the values of u and v?
I need to know how much in the x, y, and z direction each vector is going.
The magnitude.
You need to know the magnitude of u times the magnitude of v. If the magnitude of u times the magnitude of v is 8, then 7 relative to that number, is close to that number. So then these two are, what's the conclusion? Are they relatively parallel or relatively perpendicular?
Relatively parallel.
Relatively parallel. They'd be exactly parallel if this was 8 as well as this one. Okay? But they're close to being parallel, and they're close to going in the same direction. If this was a negative 7, they'd be close to being parallel but going in opposite directions. And so, and both of them are relative to this number. The scalar part of this, relative to this, tells you, and you can say how much they're perpendicular, or you can also word that as what's the efficiency of the turning force. Okay. And it has to do with torque for the cross product. And what direction is the vector in? You get a vector that's a result of this.
It's going to be perpendicular to u and v.
And one more thing about that.
Perpendicular by the right-hand rule, maybe?
Yeah, there's two ways that you can be perpendicular to both of those. Okay. So it's going to be perpendicular to the plane that those two make, and you can go in either direction perpendicular to that plane. All right. And, all right. What else? Let's move on from vectors.
Like, maybe vector valued functions, and, you know, integrating and deriving and taking limits and stuff.
So, vector value functions, what are they?
It's like a function with maybe a real number as an input, or two real numbers as an input, and a vector as an output.
Okay. So, they go maybe a real number as an input and a vector as an output. And so we often use t, and then we might have, you know, t sine of t or something like this. And when we did these, we came up with, what do we call these curves? Especially in 3-space.
Parametric equation, parametric function.
Equations. So, and that's saying x is equal to this and y is equal to this. That makes parametric equations. We also call these space curves. When you graph it, especially if it's in 3-space. Anything about these vector value functions that stands out that you might want to mention?
It's like really easy to find the length of the curve with the vector valued function.
Length L equals what?
It's the integral of the magnitude of r prime of t dt from like a to b, I guess.
Okay. So, nice intuitive formula, and this is really the speed, and the length just depends on how fast you're going. And Anything else? Should we go on to a new? What's something else that we did?
And I don't know, my mind is just scattered around. I cannot think of any particular subject at the moment. I, I wish I could remember everything.
All right, so if you can see my screen, look on the right side here, showing the names of the sections that we covered. And then, what's kind of the next major topic that we had after this?
I think it would be like derivatives of multivariable functions.
Okay, well, I think I want to go back. We kind of skipped one. We went to length of curves. This one here, lines and planes. 3 space. Lines and planes. And to remember how you get the equation of a line and how you get the equation of a plane, it is quite significant. And I'm just going to go over a super quick review of that. So, if you have here's a point, P, and then you have a direction vector, V. So, the line comes from P plus all multiples of V. Okay. And this could be, a general this. And then the planes is different. For a plane, equation of the plane, you want to have a point in the plane P, and then you want a vector that's perpendicular to the plane. And the vector that's perpendicular to the plane so then we take a general point over here, x, y, z. That general point can also be thought of as a vector. Okay, and this general point, x, y, z minus p, gives you a vector in the plane. What color should I use here? When you subtract these two, you get a vector in the plane. When you dot product that with this normal to the plane, we'll call that n for a moment, you are going to get the dot product of two things. Now that has to do with the turning power, that's maximum turning power. So, but if you, that's the curl. The dot product would be 0 between these two, and the dot product is what's going to get you. So this is the dot product vector in the plane with a vector perpendicular to the plane. And then you get 0. That's how you come up with the equation of a plane. All right, and anything else? Okay, and Rowan, you were saying the calculus of different vector stuff?
Well, like, I think it's pretty simple, like, to take the derivative of a vector valued function, you just differentiate the individual components.
Yeah.
So, yeah.
Okay. And then the other stuff that we had is a little bit more recent. And let me just mention a few things here, and then I think that's all we're going to do with the practice quiz part today. Is so level curve, graphs and level curves. So in particular, the relationship between level curves and gradients. And remember that the difficult part with the gradient, I think, is that it's in the domain of the function. So it's kind of like, you know, you're on the floor looking at this glass-shaped surface above you. And sometimes you're on that surface, and then you're kind of wondering, you know, what the direction do I go to in which direction do I travel in order to increase my height the fastest? And then you project down onto the XY plane, onto the floor, and then the gradient is a vector in the domain that points in the direction of fastest increase. And it'll always be perpendicular to the level curve through that individual point. And then directional derivatives. We use the gradient to get a shortcut for finding directional derivative. Dot producting the gradient with a unit vector in the direction that we're taking the directional derivative. And tangent planes and linear approximations. We're getting kind of more recent, but I like to think of projecting out into the future. Take the current height plus, and then we have to say, all right, what's my function doing? How sensitive is it to a change in x? And then evaluate it at a point times how far we moved from the point x0 and so on. And we do the same thing with fy. X0, y0, x0, y0, y minus y0 to get these equations of these planes. Max and minimum problems, that was showing up on the last test, and I think this other stuff is kind of more recent. Alright, so let's go to today's topic, which is divergence. And so the title is Divergence and Curl, and it's unfortunate that this got saved to the last day because it's really cool stuff. Alright, the divergence. We will investigate divergence first in 2-space, where we can draw pictures nice and easy. The vector field f of xy is fg. So some, little f is some function of xy, and same with little g. Now, and we use those functions to, draw pictures of vector fields f. little arrow emanating from all these different points. Imagine a cloud of gas. Would the gas condense, increase density, or expand, where it would be decreasing density, under influence of the following vector fields? So, A, the vector field is F equals x0, and I've drawn a picture of that vector field. So notice that every arrow, all these blue arrows, don't depend on your height. When you change the height, it stays the same because there's no y in this. But the further you move to the right, the bigger the x component is, the more the graph goes to the right. Every vector has a y component of 0, meaning it's horizontal, but the ones that start further from the x-axis go further. And the ones really close to the x-axis hardly go anywhere. These shouldn't be kind of bumped right up against the x-axis, and they should be a little bit over. Sorry about that. Because right at the x-axis it would be a vector of 0. All right, and when they're negative, they go in the negative direction. Positive, they go in the positive direction. All right, so in your group chat, answer the question, if a gas is under the influence of this vector field, like this is kind of wind patterns or something like this, will it condense or expand? All right, group 2, what do you say for this one?
I figured that it was
down.
Go ahead.
I figured that it was going to expand since it's like the vectors move outward, and so it kind of like you could say blow the gas outwards
That's
instead of
right.
bringing it together.
That's right. So this one is going to expand. Now we also have another name for that. We're going to call it positive divergence. Okay, so it diverges. They get farther and farther apart from each other, the individual molecules. All right, let's go to this next one. Oh, before we go to the next one, notice each time we increase x by 1, the horizontal component of the vectors of f increase, producing expansion, which we call positive divergence. All right, so every time you increase the x by 1, you move to the right. You might have been up here, you're moving to the right. Doesn't matter what horizontal line, what vertical position you're at. As you move to the right 1, the x component of the vector increases. Each time we increase y by 1, the vertical component of the vectors of f, this should be bold, stay the same. They stay at 0. So the partial of f with respect to y equals 0. Oh, each time we increase y by 1, this is not f with respect to y, this is g with respect to y. Because remember, cap F was little f, little g. This has no effect on the divergence. All right, let's go to the next situation. Cap F equals 0x. And this is what it looks like. And this time, the horizontal portion of every vector is 0. So all the vectors are strictly vertical. And the verticalness depends on your x position. When you're at an x coordinate of 1/2, the height of every vector is 1/2. When your x coordinate is 2, the height of every vector is 2. Of course, every vector doesn't go to the right at all, it goes strictly vertical. When you go out to 4 over, the height of every vector is 4. And when you're at negative values of x, the same thing happens, but you're pointing down. So, look at this, decide whether you're having, whether the gas is going to expand or condense. In this situation, type that into your group chat. Okay, group 1, expand or condense?
Also expand.
The gas expand. Can you explain why?
Not really. I mean, I just feel like if you were to place, like if all these vectors represent some force, you know, like the particles of gas that are farther away are going to be accelerated more quickly than the ones in the center. And so in general, everything's going to spread out. And like the ones at the center will never be able to be as far away as the ones on the edge. So it can never really, like,
I don't know, maybe it's that there's no changes because it looks like its vector is the plus side and minus side, it cancels off.
Yisu, you're saying not expand, but divergence is 0? So it's not negative, compressing, not positive, expanding, but divergence is 0? Also,
Yeah, I guess that's what I'm saying.
that's what your instincts are telling you? Anybody else have an opinion on this?
I was kind of thinking the same thing as Hisu because it's definitely not, what was the word? Condensing, but it's really not expanding either. It's just kind of flowing away, kind of like a stream would in a way.
Yes. All right. So, what Rowan was saying about, further over to the right, these certainly are moving faster. But if they started close together in this little stream, they're going to stay. Think of traffic. This is just traffic moving faster, and this is traffic moving slower in cars. And you're going to stay the same distance away from the car in front of you, though, because everybody's moving the same speed in every little track. But all the little tracks are different. You move to the right and you're in a different track. But there's no forces that is going to move you off of the track that you're on. Once you're on a track, you're just going to stay on that track. So this one is this. So I think this was neat that we got this answer first, because that had been my first instinct too. It's probably expanding. But a more careful analysis brings us to this. All right, now, and here, notice, if left alone, gas would move rather uniformly in small streams, neither condensing nor expanding. Each time, technical, should be an N. Each time we increase x by 1, so imagine anywhere here, you increase the x by 1, you're moving to the right. So we increase x by 1, the vertical component of f increases. And this does not produce divergence, but causes rotation. If you were increasing the x's by 1. If you were increasing the x's by 1, you would have a rotational force acting on you, not a divergence, not an expansion or a compression force, but a turning force. And this should be bold and italics. Okay, not producing but causing rotation. Each time y increases by 1, the vertical component of the vectors of f stay the same. Every time y increases by 1, the vertical components increase by 1, stay the same. So, fx, we're saying is 0. Every time you increase the x by 1, because that's a derivative with respect to x, but the f is the x component of the vector field, that doesn't change. And when you increase the y by 1, the y component of the vector field f stays the same. And the total divergence is 0. So, both times when I have this little paragraph, I wind up looking at fx, little f, its derivative with respect to x, and then little g with respect to y. And let's look at the next one. Let's see. Cap f is negative y x. And I have a picture of that. And, you know, when you see just the vectors, it's kind of handy to see that on this little red circle, you are going to get pushed around like this. And on this little red circle, you know, your tangent to the circle, the vectors are tangent to that circle all the same distance, which is the same as the radius of that circle. Same as the radius of this circle is all these. And so this is what's happening here, and this is all the way at all points in the plane. Discuss in your group chats very quickly. Will this compress or expand the gas? Okay, group 2, what's your instinct?
I'm thinking it's probably the same as the last one.
So,
Since it's just kind of floating around in circles, but it's not really condensing.
your instinct is that divergence is 0?
Yeah.
Everybody agree with that? Anybody have a different opinion?
I think I do have a different opinion.
Okay, what is it?
If we start at 0, 0, the gas doesn't go anywhere. I agree with that much.
Okay.
However, if we start at 0, 1, If we start at 0.01, we'll go to 1, 1, correct? Because that's where the force field, our force field has us headed. Now, once we are at 1, 1, 1 by negative 1, we will move out to 0, 2.
Okay,
Once we're at
so
0,
what
2.
you're conjecturing is if you
Yes.
start at this point here,
And then step upward.
if you start here, that you would wind up just moving horizontally all the way. No? Or you would,
No?
now you'd start moving horizontally right here, out of that,
And then you'd change diagonally.
and then you'd arc like this.
In effect, yes, but not quite the precise curve that you're drawing.
Okay, but something like that.
That is the end behavior I see.
Okay, and if that's the case, do you get expansion or compression?
I think we get expansion.
Because
Everything doesn't really move in a tight uniform circle. The farther away you get from the origin, the further you go. And once you're out from the origin from a little bit, you don't stop going away from the origin.
all right, what do y'all think of Cameron's conjecture then, that the divergence is positive because of this effect?
I would agree with that. I feel like it's almost like a reverse whirlpool, and I would say like a whirlpool would converge, but this is like going the other way, so it's diverging.
Why is it reverse?
Because like a typical whirlpool, you might like put like a little ball somewhere in it, and it would drift to the center of the whirlpool. And I feel like if you put anything anywhere, and even if it's like just slightly off from zero, it's going to spin outward and away forever.
Okay, and all right, so y'all are bringing up some interesting points that may well be true. I can't see the illogic of that. But let me tell you the technical thing. This is going to have a divergence of 0. And in that sense, it's almost as if this is kind of assuming that things with this kind of influence would stay in their little circles. Everything would stay in their little circle. But their instantaneous direction of travel, just because the instantaneous direction of travel is that, doesn't mean it's going to move that way. You could kind of think of this as orbits, and this is a force of, I think just because the instantaneous is there, you have some other, but then you'd need another force pulling it in towards the center. But as soon as you move over, the force changes. It's too complicated for me to figure out now. Yeah, you guys bring up valid points. But let me just tell you, the technical reading of this is divergence of 0, and I'll have to look into it. Nobody's ever brought this up before, about this thing kind of curling slowly away from the center. I like the way you guys were reasoning. And maybe I'll look into this into the future and come up with a little better understanding myself. All right, let's go down to this explanation. Notice, there is only an added rotational effect from increasing x by 1 or from increasing y by 1. Wherever you're at, if you increase your x by 1, particularly if you're on the x-axis, if you increase the x by 1, you've increased the y, but you haven't increased anything in the x direction by 1. When you move in the x direction, if you also increase your speed in the x direction, that's going to make you get further apart or closer together. But this is not. It just has a turning force that increases. So, we're increasing y by 1. Fx, so the fx is 0 and gy is 0, and then there's no divergence. Alright, so let's go to number 2. The divergence of f. Now remember, f is this. And it says the divergence of f is you take the partial of the first function with respect to x and the partial of the second function with respect to y, and you add them together. And that gives you what we're going to call the divergence of f. This simply tells us if we have expansion, which is positive diversion, compression, or neither, and positive diversion would be, positive divergence is if you get a positive number out of this. And this is from the textbook, the divergence in 3 space of a vector field, little f, little g, little h, has, notice the shortcut notation that gets used for it. It does partial, it has this del dot f. Now, the del, it's thinking that, remember when we did del of like phi? This is the partial of phi with respect to x, and you make a vector out of this. Okay, so if you kind of separated out this del, it looks like it's in this parts. And then there's the phi. So in this sense, we're using this del to mean this. Partial with respect to x, partial with respect to y, partial with respect to z. Now, if you don't have the partial of what you're taking, this doesn't make any sense. But this is kind of a handy notation when you dot this with this f, which is f, g, h. The dot product, this, you put together with this, you get that. And then you sum them all up. And so this is a handy notation for the divergence of f to quickly come up with this. So, and then if the divergence of f is 0, we call the vector field source-free. Divergence positive, we call it positive divergence, and it's equivalent to like a gas would expand. All right. And let's look at an example of this. So, here the little f is x squared, the little g is negative 2xy. And that's the vector field. It takes a lot of time to graph these vector fields by hand, so I went to this geoalgebra.org website to get this vector field quickly graphed. And, you know, if I go to GeoGebra.org and I try to get to a vector field, I had a hard time. But if I Googled vector field graphing and then this site, GeoGebra, I clicked on that link, it sent me to the portion of this program that graphs vector fields, and it was really then easy to use. And so this vector field looks like this. So when it's got graphed, it looks like this. And we're going to compute the divergence of f. And the divergence of f at some particular points, and then we'll look at the components of the points. Look at each component of the divergence at these particular points. Alright, so let's start with the divergence of f. Now, divergence of f is a scalar. It's the partial with respect to x of the first function, that's the little f. And this is the little g. And this derivative is 2x. This derivative with respect to y, you treat the negative 2x as a constant. You get this. And the divergence of this vector field, although it's complicated, its divergence is 0. Now, we'll get a little insight into why the divergence of this is 0. It seems like, wow, you know, if you are a gas in here, you're going to be moving along here, and if I was a gas here, look at, I'm going to get longer and longer vectors. Wouldn't I be moving further and further apart? Well, let's look. Compute the divergence of f at the point 1, 3. So let me write that here. The divergence of f evaluated at the point 1, 3. Now I know I'm going to get 0 because it's 0 everywhere. But let's put it into this formula. It's going to be 2 times the x coordinate and this is the first part, and then negative 2 times the x coordinate again. And it's going to give me 0. Now, what does this, now the point 1, 3, 1 over 3 up, here. Right. This part right here, this came from f. So what does it mean? As think of this for a moment. As you move 1 unit, because any derivative with respect to x, any partial derivative with respect to x, says how does now the f, the little f, was the x squared. Partial of that with respect to x. This governs the x component of any of these vectors. Now, as you move to the right, if the x components of the vectors get bigger, you're going to be expanding. And the vectors are going to get, and the particles are going to get further and further apart. If you move to the right, every time you move to the right one, the x components of the vectors get smaller, then you're going to, it'd be like driving in traffic, and it gets more and more congested, and then you're going to be condensing. The gas will condense. So if we think of moving to the right here, and then look at the x component of each of these vectors. Now the x component of this vector is this little, I'm going to blow it up here. The x component of this, I'm going to blow it up even more. There's the x component of that vector. As I move to the right, see the x components of each vector are getting longer. I have to move up a little bit to follow these vector things, but basically I'm moving to the right, and I'm seeing that the x components of the vectors are getting longer and longer, and that is expansion. So the factor regarding this is positive divergence. But let's look as we go in the y direction. This is g of y. Now the g of y turns out to be -2. So that, what does this mean? The g came from the -2xy over here. As I move in the positive y direction from this point, if the vectors are getting longer and longer, I would be, if the y components of these vectors are getting bigger and bigger, I would be expanding. But let's blow this up and look. Each of these vectors, as I move in the y direction, the y components of the vectors are getting bigger, but bigger negative, because they're going down. So as I move that way, now this is condensing, and it's maybe easier to see if I went in the other direction. They're getting shorter, and we're condensing. And you put those two together, and so from here you would say, hey, my path looks like I would be traveling from this point. It looks like I'd be traveling kind of an arc of something like this. And I'd be getting longer and longer vectors. But as far as x goes, yes, I'm getting longer and longer. But as far as y goes, I'm getting shorter and shorter as I go. And those two neutralize each other out, and I have a total divergence of 0. Alright, so you do the next one. At the point -3, 2, find that point on the graph, find the two components, and explain the divergence at that point. So let me give you a couple minutes to look at that yourselves. Okay, so at -3, 2, I'm right here. The divergence of F evaluated at -3, 2 is 2 times the x coordinate plus -2 times the x coordinate. Alright, so this turns out to be -6 and this is +6. So what's it saying at this point? As I move in the direction of the positive x-axis, from this point, as I move in this direction, my x component of each vector is getting shorter. I am compressing. So that's why this is negative. And as I move in the y direction, let's go, here's the nearest ones. The y component of these vectors is getting larger. And these two forces are going to balance each other out. Now, at an individual point, we have to actually take these things infinitely small. And the divergence, amazingly enough, this algebraic stuff takes that all into account and tells you what the divergence infinitely close to this point is it is a total sum of 0. It's pretty incredible stuff. And, alright, we are at a break point. So, let's start again. At 6:34 p.m. And anybody need to speak with me before I take my break? awesome! Exclamation mark. Mom will be so excited. So am I. Perhaps we should play a board game. My deck was originally all green, comma, using the few green junk creatures and pumping them up. But now I am mixing it with red. Quinn's appointment was today. Don't really know how it went. Period. Alright, my arithmetic skills were suffering there. I gave us a 5-minute break originally, 6:34. I meant to give it a 15-minute break like normal. Alright, and so let's do number 4 on divergence. And let's get rid of this so I have a little space here. On a 3-space function, compute the divergence of f. So the divergence of f is a simple task. You just take the partial respect to x of the first one, so it's 2x. Partial respect to y of the second one, negative 2x. And then, so this is the same function that we just had for the first 2 components. But now it's got an additional third component. And we take the partial respect to z of that. And so the y is a constant, so it's 2yz. Alright, these two kill each other off, and we get 2yz. Alright, so in this one, we have 3 contributions to the divergence in 3 space. As we increase in the x direction, as we increase in the y, or as we move in the y direction, and as we move in the z direction. The x and y directions cancel each other out as far as divergence goes. But the z direction provides us this divergence. So when we compute these things, 2yz, the divergence of f evaluated at 131 is this 2yz 231, which is 6, and the divergence of f calculated at negative 3, 2, 1 is the x coordinate doesn't make a difference. It's just 2 times the y times the z, and it gives you this. And so in general, we get a function for the divergence at any point. And then we use that to find divergence at specific points. Sometimes we can deduce things just from this, like that the x component has no effect on, now it seemed like over here it was the y component that disappeared and the 2x components were, critical effect. And they kind of had that critical effect and then it disappeared, and the only thing that matters is the y and the z in the total divergence. So we can get some big kind of observations from this function, but very often we use it at specific places and then just find out what the divergence at particular points are, and it can vary according to where we are. Alright, so that's a quick introduction into divergence, and we're going to move on to curl. Any questions or comments on divergence before we move on to curl?
I guess maybe I missed this. What does negative divergence mean? Like, does that mean convergence or what?
Negative divergence means compressing the gas.
Okay.
Positive means expanding. And 0 is neither of that happening.
But like, if you were to say like convergence, I don't know if that's like a thing that's used, but would it be the same as negative divergence?
Oh, yeah. The divergence is negative. We would tend to say compression instead of divergence, instead of convergence instead of divergence. Yeah.
Okay, thank you.
Good point. All right. Anything else? Comments or questions on divergence? Or we leave that and go to curl. All right. Curl. Basically, the curl of a vector field F is the rotational effect of the vector field F. So, I'm going to have you, and this is a task you have with your group, is create a vector field F that has curl. So it has some kind of rotation of the following form. And in A, the form is F equals A1I plus A2J plus A sub 3K, where A1, A2, and A3 are constants. So, create a vector field, F, that has curl or rotation that has that form. Okay, group 1, were you able to do that?
Well, I didn't have time to write it down, but I would say that you could just kind of mix up the constants and then add some negative signs. I think that my idea for that came from the like rotational vector field where you like switch the x and the y and you make one of them negative.
Okay, so let's try this. And I'll change the format here so I can write it a little quicker. So make some of them negative like this.
Yeah, yeah.
Okay. Everybody agree this will have rotation?
Well, I feel like we're gonna need some variables in there, like maybe x, y, and z.
But you're not allowed to. It has to be of this form, where there's
Um,
just constants.
Then I'm not sure because that's not gonna have rotation because it's gonna be the constant vector everywhere.
Ah, this is a constant vector everywhere. If it's a constant vector everywhere, and I think we had pictures of that. Conservative. It's like this. Constant everywhere, but it's in 3 space, but it's still the same essential picture as this. And so it'll have no rotational effect. So, what does it tell us? This task is impossible. If you're confined to constants, you cannot create a vector field that rotates, that has a rotational effect. All right, let's go to part B. Create a vector field that has this format. And I'll use this notation this time. F1 of x. F2 is a different function, but it only has y in it. And F3 is a different function, but it only has z's in it. It could also have constants, like +5 or something like this. It's a function of x. The first function is just a function of x. Second function, it's just a function of y. Third function is just a function of z. Create a vector field with rotational effect that has this format. Okay, group 2. Any ideas for this?
I wasn't really too sure, and Cameron didn't have any guesses either.
Alright, so you two are a bit stuck on how to do this. Let me just make up a random one. X squared, y plus 3, square root of z minus 2. Okay. Now, could this have any rotational effect? To answer that question, I'm going to take a simpler function. And let me get some more space here. Could this have a rotational effect? All right. Let's look at this situation. If f is such that the partial of f with respect to x gives you only a function of x in front of I, and then zeros I, this is j, this is k, zeros elsewhere. Then increasing x by 1 produces only a change in the vectors and these are vectors of f. Only a change in the vectors of f in intensity in the x-axis direction. Okay, so because we're understanding what it means to be a derivative with respect to x, whether it's a regular derivative or partial derivative, it means that's how does this change every time we increase x by 1? Well, this is telling us that when we increase x by 1, or move 1 unit in the x-axis direction from where we're at, the only thing that's going to change in the vectors is the intensity of the x component. The y and the z components of the vectors stay identical. Now, the graphical interpretation of that is like this. When I move 1 unit in the x direction, I can't change the y component and make it go further to the right or further to the left. I got to keep it exactly in the same direction as far as y and z goes. The only thing that changes as I move in the x direction is the intensity of the x component. Now the x component could get bigger, in which case the gas is going to expand. But it's not going to produce rotation. That's what this curl is about. We're looking at rotation. We focused on this in divergence. When we take the first function of f, and when we take its partial respect to x, that causes expansion or compression. If they get bigger, we're expanding. If they get smaller, we're compressing. Positive divergence, negative divergence. But when we want rotational effect, we can't get any by doing this. Okay, so it turns out this is impossible as well. Under these conditions, you cannot create rotation. All right, so sometimes the easiest way to figure out what something is to figure out what it isn't and how you can't get it. And if you're stuck with all the vectors being in the same direction, you can't get rotation. And if each component of the function f, the vector function f, can only have its own letter. The first component can only have x, the second component can only have y, the third component can only have z, then you can't get any rotation either. We're starting to see how rotation comes about. It's from mixing up these letters. Move a y into the x or a x into the z or something like that. That's how you get rotation. And that's kind of consistent with what we were seeing over here when we had this vector, when you mix the x and the y, we got rotation. In the x position we put the y, in the y position we put the x, and that's what gives you rotation. Alright. Now, we're finally ready. I will create a vector field with curl, rotation. So, now what this means is, imagine your f, function f, is f, let's do it like this, f of x, y, z, comma, g of x, y, z, h of x, y, z. Right. And we're going to have f such that the partial of g, partial of g with respect to x is going to be positive. Now, what this means is, imagine there were little rectangles that each vector could fit into. And each vector starts at the back corner, upper left-hand corner of the rectangle. And what the vector fields of f would do is, as we move, see, this is how this part, how the y components of the vectors of f change as x increases by 1. Now, as x increases by 1, we're moving in the x direction. As we move in the x direction, the y components of these vectors, look at the y component, I have to blow this up to be able to draw on it. The y component has to be getting larger, because that's what the g is. The g is the y components of each of these vectors. And so, what if the partial of g with respect to x is greater than 0, then the y component is getting larger as we move in the positive x direction. Okay. This, we're going to say, it curls from the x-axis toward the line y equals x. Now the line y equals x was a dotted red line here. And we can kind of see this kind of curling happen in these vectors where as we go there, we're kind of curling. As we go from the x-axis towards that. Now, let's do another one. This is my vector function f, vector field f. And now I'm going to have this situation with partial of f with respect to y being greater than 0. Now, whenever you take one of these with respect to, see, because this is kind of the x position, the x, y, z position. If you take one of these functions and you take its partial with respect to one of the other two letters, y or z, f with respect to either y or z, and as long as this is non-zero, you're going to create some kind of turning force. So we have our rectangles this way. Now why did I place the rectangles as moving in the y-axis direction? Because the derivative with respect to y means as we increase y by 1, what's happening to the x component of each of the vectors? Now, the x component is parallel to the x-axis. The x component of this vector is little itty-bitty. The x component of this vector is bigger. The x component of this vector is bigger. As we move in the positive y-axis direction, the x components of each vector increase, and we say that we are curls from the y-axis toward the line y equals x. Okay, and let's get a little more space here. That didn't work. Now, what we're going to see is that the partial of g with respect to x and the negative of the partial of f with respect to y curl in the same direction. So let's look at this. The partial g with respect to x, when that was positive, we curled towards the line y equals x. Partial of f with respect to y curled in the opposite direction, from the y-axis toward the line y equals x. One was curling like clockwise and the other counterclockwise, or however you see that. So if you take the negative of the second one, then instead of going this direction, it'll curl that way. So to get them to go in the same direction, I put the negative sign on one of them. So if rotating, let me get to where I type this. Make it a little bit bigger. If rotating from the x-axis toward the y-axis is called a positive rotation. Now this direction is natural for us to call positive, because when you were in trig, let me remind you in trig, when you had an angle theta, you called this the positive direction. but that's rotating from the x-axis toward the y-axis. Okay, so it's consistent with what we've been doing all along. Rotating causes positive, it's called a positive rotation. Then note that the K component, now K, let's bold that, K component and I'm going to put this K component of curl of F now curl of F is kind of has some parallels to like the cross product. It is going to be a vector. So I like to show that, although people don't typically put this thing in front of that. I like to do that. And textbooks can bold that to kind of emphasize that. All right. Now, this is going to have something times I plus something times j plus, now this is the part that we can fill in. Okay. Where this is going to be the rotational effect that we're going to be getting, and it's going to be partial of g with respect to x plus the negative of the partial of f with respect to y. And that will be the rotational effect in the xy plane. But why do we put that in front of the component k? Well, kind of like we did when we were doing cross products. That turning effect, that would turn in a screw perpendicular to the plane that we're in. And we wind up doing the similar thing here, is that in the xy plane, this is going to be now the textbook is going to put a subtraction sign here. I put it over here to just emphasize that we wanted two things going in the same direction, the amount of turning force. And that's, these two are going in the same direction. And so we wind up getting the curl, and we do the similar kind of thing with what we just did by isolating what's happening in the xy plane and putting that in front of the k component. Similar thing happens to the other two components. And what we get, oh, by the way, let me put this. And if my vision had lasted longer, I would have put a lot of this into the OneNote beforehand. But it's getting towards the end of the semester and I had too many things to do, and I have vision difficulties and my vision gave out on me. So that's why I have to write more today. This right here is the direction perpendicular to the plane of rotation. turns out to be the strength of rotation. A bigger number, a stronger rotational force. Small number, a weak rotational force. And so let's go down here. All right, so I had to just clip these things from my notes as well. So while the divergence of F is a very simple idea, you just take the partials and you add them up. The curl of F is different. The curl of F, now this had this kind of notation. We could shortcut it with the dot product. This one has a shortcut notation, the del, which is this, cross product F. And this is the shortcut way we'll figure out the curl of F. And just like we did with cross products, we put I, J, K up top, and we put this one, if it was A dot A cross B, this would go in this row, this goes in this row. And then, if you take the first term, I, eliminate its row and column, take the determinant of this matrix, partial of H with respect to Y, minus the partial. So when you're doing the I, you get the other two, the G and the H. When you're doing the J, you get the mixed partials with the other ones. When you're doing the J, you don't use Y at all. There's no single Y's, nor do you use the letter G at all. And so it's got to be partial of F with respect to Z and the partial of H with respect to X. Now the order of the subtraction would be hard to remember, but doing this just does it automatically for you. That's why this shortcut is so awesome for this. And then this K is what we were just figuring out before. G sub X minus F sub Y. Okay. In a two-space vector field, the curl would just go, it would just be this one right here. What we usually do though is we don't work in a two-space vector field when we take curls. We put it in a three-space. Because you wind up getting in three-space anyway, because you got a K component. And so you just place it into three-space from the beginning, and you make the other dimensions 0 if they weren't there. And so this gets us into the curl. And let me pause. Any questions? Okay. Now, if a vector field is conservative, then line integrals in this vector field are, and you fill in the blank. So go to your group chat and type in what you think should go into this blank. But don't type it, don't hit enter quite yet. At my cue, I'll have you put enter, and then I'll ask a group. Okay, go ahead and hit enter. Group 1, any ideas? How would I fill in this sentence?
I would say path independent.
Very nice. Maybe that's an E. Don't trust my spelling. Path independent. Doesn't matter how you get from one point to the other point. Okay. Type in the answer you think to this question. How can you tell if a vector field is conservative? Go ahead and hit enter. Group 2, how would you answer this? How can you tell if a vector field is conservative? You can pass if you want.
Got nothing.
Nothing? Okay. How can you tell if it's conservative? There's the old way to answer this, which is there is a potential function phi such that the gradient
The derivative is equal to the vector.
equals f. That's right. That was one way to answer this. Then there was an updated answer to that. Does anybody know a little more specific way to answer that?
You could say the mixed derivatives of phi need to be equal to one another.
The mixed partials. So one answer was this. Are equal. Okay. Now, on the mixed partials, let's go back in a two-space vector field. These are the mixed partials right here. That's because the f was also so the mixed partials of f are equal. Now we're going to get a third way to look at this, but we'll come back to this. Okay. What's the connection between the curl of a vector field and whether or not the vector field is a conservative vector field? And type your answer into your group chat. If you have any guess about this. Right now it would just be a guess or a possible intuition. Okay, go ahead and hit enter. And let me open the floor. Anybody see anything in their group chat or anything that might be an answer to this?
So I guess that if it has curl, it's not conservative.
Ah, if it has curl, F has curl. F not conservative.
I came up with a different answer.
Okay, what did you come up with?
To help showcase my answer, can I ask you to scroll up to a prior vector field that we looked at? Up, up. Close that one.
That one, yeah.
I think that this vector field has curl, but this vector field is conservative. So I think the difference between a vector field that has curl and is not conservative, vector that has curl and is conservative, is that a vector field that has curl and is not conservative would have a curl that is that has a motion carrying through more than one quadrant.
I don't think this field is, in fact, conservative though, because we calculated the mixed derivatives and one was 2x and the other was negative 2x. So I think I'm going to agree with Matt.
Okay, it could have been my bad misunderstanding this then.
All right. You know, it's that kind of way that we find out new stuff. When we're inside something very new, the misunderstandings are just as common as the understandings, and to slowly filter them out. But in fact, some of the most creative things happen is when you don't have too big of a filter and you let yourself go through the misunderstandings to finally come to what is a big insight. And so let's come back down here. So there's a theorem. F is conservative. Let me type this in. F is conservative if and only if curl of F is zero, is the zero vector. And let's bold these guys. And I could even do curl, because when you do the curl, you get a vector. If the curl of F is the zero vector. All right. And it all has to do with rotation. When you are getting a conservative vector field, it turns out that to be conservative means there's no rotational impact on this. Or the rotational impacts in the various parts are canceling out. And let's go back here in two-space. Here are the, in two-space vector field, the curl of F is just the difference of the mixed partials. But if this difference is zero, then that means this mixed partial and this mixed partial are equal. And so if the mixed partials are equal, then you're conservative. That's also saying if the curl is zero, you are conservative. And that's also saying if there's no rotation, then your line integrals are independent of path. And that's the key idea to that path independence, is it can't be rotational. If there's rotational effects, then certainly you could go, if it's a whirlpool, going one way is not much work. Going the opposite direction, getting back to where you started with, is a ton of work. So, it's the rotational effect that's going to give you the non-independence of path.
So that one field we just looked at would not be conservative then? That big one up there? Yeah, that one.
Okay, so we did the mixed partials. Partial of f with respect to x was 2x. Partial of g with respect to y, hold it. No, those aren't the mixed partials. So if there's a
I think, yeah, I misspoke, but they are different actually, even if you calculate the right ones.
let me get rid of these f and g for a minute. And let's look at this from a different perspective. If there was a potential function phi such that the gradient of phi was going to give you f, then this is phi line through that. This is phi of x, and this is phi of y. And then the mixed partials would be phi of x, y. So I take the derivative of this with respect to y, and I would get 0. And then I do this one. You take that derivative with respect to x, and I get negative 2y, and these don't match. Therefore, it's not conservative. And therefore, this is going to have some rotational effect. And all right, let's go. Okay, f is conservative if and only if the curl of f is a zero vector. All right, true or false? The curl of the gradient of a scalar function is always 0. So let me give you a minute. Put your guess on this into your group chat. The curl of the gradient of a scalar function is always 0. Is that true or false? Okay, anybody? True or false?
I said that that would be true since the gradient of a scalar function is a conservative vector field, and so we just said that that would have to be 0.
So the curl of the gradient, of a scalar field, if you call this scalar field phi, it becomes a little bit more obvious. And now, that's conservative. Vector field. And now we take the curl of that, and yes, you're going to get, is always, I should probably have put the zero vector. Okay. And so, last thing is find the curl of f. And we got 5 minutes, so let's figure out this curl. Now, the shortcut for the curl of f is the curl of f is, we have this little device that helps us out. And when you do a cross product of A cross B, what do? You put ijk across the top. You put this A in the middle row. That's the partial with respect to x, partial with respect to y, partial with respect to z. You put this one here. Now, the only thing we have to do is replace f with x squared minus z squared. Replace g with 1. And replace h 2xz. And then I'm going to get in front of the I, knock out its row and column, and you get this. The partial with respect to y of 2xz is 0. Minus the partial with respect to z of 1 is 0. Now, let me just kind of put this in so in case you get confused and looking at it later. How do you get that 0? This was the partial with respect to y, 2xz. And this one was the partial with respect to z of 1. Then you alternate sign, minus something times j, and you delete its row and column, and you get the partial with respect to x of this, which is 2z, minus, now the partial with respect to z of this. The x squared goes away, you get minus 2z. Then plus something times the k. You eliminate this row and column. You get the partial with respect to x of 1, which is 0. And then partial with respect to y of all that, which is 0. Until you get 0i, 2z plus 2z is 4z. We just get 4z and a negative sign, negative 4zj. And that's it. The others are 0. Or it's equal to 0, negative 4z, 0. And it's a vector. And that's the curl of this vector field. And its magnitude is the square root of the sum of the squares of each of these. So the magnitude of the curl is going to wind up being 4 times the absolute value of z. And the direction of the curl is always in the direction of the y-axis, either positive or negative. And so the rotational effect is perpendicular to the y-axis, so the rotational effect really happens in the xz plane of this. And the assignment is homework 17.5. The homework problems are actually very easy ones. I didn't pick any of the tough ones. I know that you're getting ready for the final exam, as well as finishing this up. So we'll stop here for tonight. Any last questions or comments? I will see you all at the final exam.
Thank you.
Thank you.
Thank you.
You're very welcome.
Shankin.
Good night. Have a great night, everybody.
Thank
You
you.
too.
Good night.